All right, so welcome back. I'm going to keep going. I just wanted to cut it into another video because it's more logically grouped that way. So this is the start of generative versus discriminative techniques. Most of the techniques we have seen so far in the book belong to a category referred to as discriminative techniques. These techniques try to model and estimate the probability that an observation belongs to a particular class. It is effectively the boundaries among the classes that it is modeling. Strictly speaking, the algorithm tries to model the conditional probability of y, the label, given x. So, oh, you know what? Uh, Oh, so this is the error again. So this is page 153. So it's again on. This might be worth talking to the author about again. I don't know. I feel like I already told him. So like hopefully he'll get it the second time as well. He'll just look for every instance of it, but this is a big typo. This is the kind of typo that it's not good to just move on from, and it is good to report that typo because it changes the mathematical meaning of the symbols. So this is a completely incorrect correct part of the book. So it's P Y. So you got to use that pipe key, otherwise you're representing a different mathematical concept. So it's really important that the math key. So I'm gonna don't save. I think I'm gonna contact the author for this one. If I go to my messages and I click on the author's name, you are right. I'll get this fixed at some point. Thanks. Found it on page. You know what? I feel like. Oh, uh, found it again on page 153. And let me make sure that it was a 5. Nope, it's 143. And then I'll include a screenshot. Oops. And this has to be a highlighter. Highlighted in red. There we go. There we go. All right, that'll help him out. Then I've only seen it twice, so it's I think that'll help him out a lot. A different set of techniques can reach the same goal via a different path. First of all, try to model each class's characteristics and behavior in a way that could generate new observations of each class. This is why they are called generative, because they model the laws that drive the observations in each class. Mathematically speaking, it is about obtaining a model for the distribution of, and it's just going to be that way until the author corrects it. I don't need to notify him about every single instance, but I thought it was fair to, it's 100 pages later, so like it might be hard to find every. So I thought it was fair to notify one more time for that. So it is about obtaining the model, a model for the distribution of p x, and the x and the y are flipped now, but that's probably valid. The only thing that's really not valid here that does have to be corrected is this is a pipe key, because this does not mean division. It's not only is it a different mathematical concept than division, it's actually an incorrect typo character. It's meant to be a pipe, not a forward slash. Therefore, given a class Y, it is possible to obtain the probability for each possible point. Effectively, we are obtaining the distribution for such a class. Then it is possible to estimate the probability of the class Y given a specific point X using Bayes' theorem rules. There is historically a particular controversy about which approach is better. One of the side effects of the generative approach is that you not only learn to differentiate classes, but also to generate them, because it is based on the knowledge of the distribution for each class. With that knowledge, new observations can be generated following such distribution. Generative techniques such as Bayesian networks are fundamental for causal inference use cases, which are extremely important in our network and cloud scenarios. Why did this failure happen? Who got impacted by this failure? What will happen if I make this change, etc. Autoregressive models, time series prediction based on past values, are also fundamentally a generation technique, as they aim to generate new future samples by trying to model the behavior of the previous observations. In the few past years, generative techniques have gained strong momentum because they can be used to generate new data. Neural network architectures such as GANs, generative adversarial networks, are at the heart of many fake/new image or video or audio generation techniques, leveraging deep learning techniques and large available cloud computing resources. They are producing astonishingly realistic results. We will review in the next section a few of these generation or generative techniques. These techniques are being used in the context of network and cloud to generate new data in lab or simulation scenarios that can be used to evaluate software or network designs. The possibility to generate highly realistic data is not limited to images, video, or audio, but to any data. Therefore, we can leverage generative algorithms to tackle the long-standing problem in networking and the cloud, which is the lack of data to test in the lab and validate solutions. All right, so the next section is generative techniques. So I'll advance the bookmark. And this might be all I can do this morning. I'm running out of time. I want to take some time for other things. So, yep, that's it for all the videos for this morning. So just a short one. And when I come back next, it'll be generation techniques.